gave a colloquium. It was about harmonic measure and connections to Descendants-Dauphin. So that had some slight connection to algebraic geometry, but this time there's a slight collection to differential geometry. And in fact, a lot of people in the audience like Claude and Leon, and I don't know if John Morgan is here, Dror and others have helped me figure this stuff out. So I appreciate that. And if I forget to mention you by name explicitly, you are written in the thanks of the preprint. So it is in writing somewhere. So the plan for today is to give a little bit of motivation and some connections to different areas to try to impress you that it's an interesting topic. Then I'm actually going to define this class of Weil-Petersson curves. We won't get to that for about 10 or 15 minutes at least. And then I want to state half a theorem and sketch part of the proofs. And unfortunately, the theorem is too long to state in a 1-hour lecture, but we'll get through part of it. And hopefully, I thought I picked out the parts that might be most interesting to you. So the basic idea is that we're going to consider loops in the plane. And I'm going to pretend that these are interesting because of string theory. And physicists like to study loops, but they really like Hilbert spaces. And so they like the space of loops to look like a Hilbert space. And that's unfortunate because there's a really lovely theory called Teichmuller theory of closed curves. But the theory is based on the L-infinity metric. And so the universal Teichmuller space of closed loops is a Banach manifold, not a Hilbert manifold. So that's a little bit unfortunate because Teichmuller theory then isn't really ideally suited for string theory. But Leon Takhtajan solved this problem. So in 2006, he and his student Teo wrote a monograph in which they gave a Hilbert manifold structure to the space of closed loops in the plane. And the questions that we're going to talk about today are about exactly this Hilbert manifold. So I like to draw a little cartoon to illustrate what they proved. Here's a picture of the space of loops. Now, the thing about their metric is that it makes this into a Hilbert manifold, but it's disconnected. And these lines represent the different connected components. For example, the square is a closed loop, and it lives in the space, and it's in some connected component. These are the things that are a finite distance away in this Weil-Petersson metric. The von Koch snowflake, that's another closed loop, another fractal. It's somewhere in the space, but it could be on a different connected component of this space. So basically, Takhtajan and Teo cut the space of loops into uncountably many different fibers, which contain different closed loops. And the question is, which ones are only a finite distance apart, which ones are in the same fiber, and which ones are in different fibers. The most interesting fiber I colored in red. It's the one in the middle here. This one is the one that contains the circle. That's sort of the most obvious closed curve. And it contains all the smooth closed curves. In fact, this one special component is the closure of all the smooth curves in the plane. And the question is, it's the closure. So there's stuff in there other than smooth curves. And the question is, what's in there besides the smooth curves? Classify, characterize the closure of the smooth curves, because that's really what what the physicists are interested in doing calculations on are basically closed loops. But to get nice theorems, it's nice to work on a complete metric space. So it's nice to take the completion of that. Now, I did not start thinking of this because Leon asked me. That might have been a good way to go. But in fact, I first became aware of this as a question from David Mumford. We were exchanging emails about another issue. And he asked me, which non-smooth curves are in the Weil-Petersson class? He's motivated from his work in computer vision and pattern recognition. The kinds of things that he does is to consider shapes and trying to classify them. One or two shapes the same or different. That's kind of a clustering problem that depends on a metric between the shapes. And in his work, he considers about half a dozen different metrics on loops, but the Weil-Petersson metric defined by Takhtajan and Teo is like one of the best. One way you can see that, these are some figures of, these are geodesics. So for example, in this picture, we're taking an ellipse, which is vertical, and an ellipse, which is kind of diagonal. And this picture connects the two of them by a geodesic in loop space. And what you might think is that if you're taking an ellipse and you want to rotate it, the easiest thing is just to rotate the ellipse. But the geodesics in Teichmuller space that they compute actually go through something which is almost circular, sort of goes round. This is another example where they have kind of a square shape with a bump and another square shape in the bump, but in the middle, there's kind of a round shape. And what this indicates is this is negative curvature of the loop space, that geodesics between points all sort of want to get close to the circle somehow. But this is what negative curvature looks like, that geodesics between distant points all sort of come to some finite distance of a base point. And so in their computations, they're mostly interested in smooth curves, but they're really interested in what kinds of things might they get as a limit of these smooth curves. And that's why they want to know what's the completion, what are the non-smooth curves in here. And so this is supposed to convince you that this is an interesting question. I have Leon's word for it, David Mumford's word. If you're a snob and that is not quite enough, august company, we can go back to Hilbert and says that such manifolds he's talking about are constituted, for example, by the possible shapes of a figure in space.
That's Riemann.
Riemann, what did I say? I meant to say Riemann. Okay, so we have a pretty good authority that studying spaces of loops or shapes is pretty important thing. But even this wasn't quite enough to get me going. I really started on the problem when I went to IPAM about 2 years ago and listened to a lecture by a young postdoc at MIT, Yilin Wang. It was entitled Loewner Energy via Brownian Loop Measure and Action Functionals of SLE and GFF Couplings. And for some reason, this made a lot more sense to me than anything else that I'd heard before on the topic. I'll explain why in about probably 10 or 20 slides. So in a couple of minutes, we'll get back to why that was sort of turned a light bulb on in my head. Just to summarize so far, there's this thing called the Weil-Petersson class of closed curve, which I haven't defined yet. But we know it's related to things like string theory and Kähler-Einstein manifolds and Teichmuller theory and pattern recognition and Brownian motion, things like that. What I'm going to do in my talk is try to convince you it's related to other things like Sobolev spaces and knot theory and geometric measure theory and hyperbolic space, minimal surfaces, something called renormalized area. And so these are the kinds of topics we're going to be talking about later today. Okay, so this ends the motivational portion of our talk. Now we're actually going to give a definition of a few things. Any questions so far? Are we okay? I have to ask the standard question, is anyone out there? Because I can't tell.
Yes, no, we're
okay. So I have this fear that, I'm just talking and I've lost my connection and there's only ether. That has happened to people.
You want us to nod?
I don't have your pictures open, so they block my view of the screen. So just ask a question every once in a while or shout something. So we don't have to know very much about quasi-conformal mappings, but I do want to mention that these are just a class of mappings from the plane to the plane. They're homeomorphisms, one-to-one onto mappings. They're a little bit better, a little bit worse rather than differentiable maps, diffeomorphisms. If you have a conformal map, small infinitesimal circles map to circles. But in QC mappings, quasi-conformal, small ellipses map to circles, but the eccentricity is not too bad. So it stays bounded. If you had a diffeomorphism, presumably this eccentricity could get worse and worse as you go off to infinity, but we're assuming it's uniformly bounded. And the eccentricity is the ratio of the major axis to the minor axis in the tangent map. So these are pictures of the tangent maps acting, they're linear maps. We're really not going to use too much about that, but one thing we should know is that the homeomorphisms are basically in one-to-one correspondence with this thing called mu. It's the fz bar derivative over f of z. And the z bar derivative, that's zero if and only if f is holomorphic. So this mu being zero is the same as having a conformal mapping. And for a mapping of the plane to the plane, that just means a linear mapping, az plus b. And so somehow the size of this mu sort of tells you how far away you are from just being a similarity, right? We will actually be more concerned with a certain special subclass of quasi-conformal. So we don't have to worry about things that are quite this general. There's a subclass of things which are biLipschitz. And so these are mappings which the distance between points is expanded or contracted by about most bounded factors. So here it's pretty clear that a round thing can only go to something that's roughly bounded eccentricity. But the biLipschitz also means you can't change the scale. A QC mapping can do this, but it can make a little tiny copy of the same thing or a great big copy. And biLipschitz maps can't do that. The Weil-Petersson maps we're going to talk about are actually quite closely related to biLipschitz mapping. So they're sort of, you don't need to know the full quasi-conformal theory to get today's talk at all. But officially, a quasi-circle is the image of a circle under one of these quasi-conformal homeomorphisms. And that's it. You have a mapping of the plane to the plane. The circle gets carried onto a Chord Arc curve. It's a special kind of Chord Arc curve because we're not allowing arbitrary homeomorphisms. They have to have this special property. That's what these are. Every smooth closed curve is a quasi-circle automatically. That's basically because these dilatations for a smooth map are bounded on a compact set. And so if we were to just restrict ourselves to a compact neighborhood of the circle, it is not too hard to see that we would have to get a quasi-circle. If I hand you a curve though, say here's a curve, whether or not you can tell it's a quasi-circle, that requires a geometric characterization. I mean, the definition is hard to check. It would be nice to have a test, something we could test and see if it works or not. For example, is this a quasi-circle? Well, it doesn't look smooth. It's the von Koch snowflake, but it does turn out that it is a quasi-circle. And the reason I know this is because if I take 2 points on here, like this one and this one, I can measure the distance between them straight, and then I can see how big is the arc that connects them. And I notice this arc, the diameter of this arc is only a constant time bigger than this arc. And that's the geometric characterization of quasi-circle. So something is a quasi-circle if when you have 2 points, the arc between them, the diameter of that arc is at most a constant times the chord distance. So the chord just means the distance between the endpoints. And so things like the von Koch snowflake satisfy this, and so we can easily check. Now, the whole point of today's talk is I'm going to define something called this Weil-Petersson class and give a definition of it. But looking at a curve, it's hard to tell whether it's in this class or not. And so what we want is a characterization like this, some test that we can apply to the curve and easily tell yes or no is the.
Could you define the chord distance here? Because
sure,
it's not the arc length along the curve.
No,
right?
it's what I've circled in green here.
Oh, I see.
It's the distance between the endpoints. So when you have an arc,
right,
the chord distance is just the distance of the straight line chord between the endpoints.
right.
And so what you're measuring here is, in some sense, how much bigger is the arc than the geodesic connecting the same points. Okay, does that make sense?
Oh, okay. I see. You're comparing it to the diameter. I've got it. Got
Yes.
it.
So you're comparing the straight line distance to the diameter of this set.
To the diameter of the set. Okay, that's
Right.
the.
Now the diameter is, let me maybe highlight this and something doesn't go away. So we're taking the diameter here. We have to take diameter because the other natural thing would be arc length. But on a fractal like the von Koch snowflake, the arc length would be infinite, whereas the diameter makes sense. But if you have a rectifiable curve, then it would make sense to ask, is the arc length comparable to the chord length? And that gives the class of chord arc curves. That's exactly what happens, that the length is dominated by the chord, and those are exactly the images of the biLipschitz mappings. So quasi-conformal images of the circle have a nice geometric characterization, and biLipschitz images have a nice characterization. And the question is, do Weil-Petersson curves have a nice characterization? And we should actually get around to defining what they are. So here it is. So this is not the definition given by Leon in his memoir, but somewhere on around page, I don't know, 60 or 70, he mentions that this is an equivalent definition, and I prefer it. So I'm going to use the equivalent definition as my starting point. So we have a QC mapping of the plane to the plane. We have our circles being mapped to a curve. For technical reasons, we are allowed to assume that the measure, that the dilatation, the thing that measures how conformal we are, is 0 out here, but maybe not 0 in the disk. Okay, so it's convenient just to assume that the mapping is conformal on the outside and not conformal on the inside of the disk. If you want to think there's a diffeomorphism, that's perfectly fine. And the definition just is that this dilatation is in L2. Now, what exactly does that mean? Because it's quasi-conformal, automatically the dilatation is bounded by 1. So the dilatation tells you how eccentric these ellipses are that get mapped to circle, and the mu is always less than or equal to 1 in absolute value. And so you'd say, well, bounded functions are square integrable, obviously, but that's for Euclidean area. This is for hyperbolic area. So in hyperbolic area, the disk has infinite area. Remember, in the disk, you have, neighborhoods, unit neighborhoods of the hyperbolic metric. They sort of get smaller as you get too close to the boundary. And so because hyperbolic area has infinite area, it's not clear that being bounded implies you're in L2. So basically, general quasi-circles correspond to bounded dilatations, and the Weil-Petersson class corresponds to bounded dilatations, which are also in L2. So they sort of tend to zero at some rate near the boundary, which is square integrable. And so informally, you know, Weil-Petersson class is to L2 as QC is to L infinity. And one of the points is that L2 is much easier to understand than L infinity. I mean, a Hilbert space is much easier than a Banach space in L infinity. So basically everything we know about quasi-circles, there should be an easier, simpler analog of it for the Weil-Petersson class. And I hope I'm going to try to convince you that that's correct. That's really true. Okay. A couple of other observations before we go on. We're going to use a couple of facts later on. One is that the Weil-Petersson class is Mobius invariant. If you were to take this thing and then apply a Mobius transformation to it, AZ plus B over CZ plus D, and get another curve, it's still Weil-Petersson. That's because this definition, this dilatation is conformally invariant. If you pre-compose or post-compose by a Mobius transformation, its absolute value doesn't change. And so being an L2 doesn't change. So this is a nice Mobius invariant class of curves. So that's one thing we're going to use later on. The next thing we're going to use is a little bit more technical. This is sort of for experts, so don't worry if it seems a little obscure. If you take a point outside the curve here, I can take its inverse image under F. So I can take its inverse image is back here. This is the point it maps to. And I can reflect it across the circle just by the map 1 over Z bar. It's the standard reflection across the circle. And I can map that forward again. And if I do this for different points, if I start with a point here, comes over here, reflects, goes across here. If I start with a point on the curve, it goes back to the curve and it goes back to itself. So there's a natural reflection across the curve that comes with this setup. And it turns out that this reflection, the curve is a fixed point for this involution of the sphere, the 2 sphere, and it's also QC. And not only that, it's biLipschitz. So I won't explain that, but that's an old theorem that if you have a quasi-circle, then there's a biLipschitz involution of the sphere, which preserves it and exchanges the 2 sides. And this is a little bit more convenient, especially for generalizations to higher dimensions, because it's a little easier to talk about biLipschitz mappings in high dimensions than quasi-conformal mappings in high dimensions. In any case, in about 10 minutes before the end of the talk, I'm going to say, do you remember the slide where I said that you were Weil-Petersson if you were a fixed point set of an involution that had this dilatation L2, and you're supposed to say, of course, we remember it. You told us to remember it. So this is the slide, that a curve is a Weil-Petersson curve if it's pointwise fixed by an involution of the sphere that exchanges the 2 sides of the curve, and that the dilatation, the distortion, is an L2 function for hyperbolic area on the complement. So this is probably the most technical looking thing I'm going to show you, or one of the most technical looking things. But I'm going to use this later on to prove that something is a Weil-Petersson curve. I'm going to show it has this property. So I'm just putting that in the bank for later on. Okay. Now let me show you a little bit about what Weil-Petersson curves look like. They're supposed to be the closure of the smooth curves. So every smooth curve is in here, plus a little bit of extra stuff. Not too much worse. Being Weil-Petersson, it turns out, implies something called asymptotically smooth. And what asymptotically smooth means that if you take 2 points and you compare the straight line between them, and you compare the chord, the arc length between them, that ratio tends to 1. So remember that chord arc meant this ratio was bounded, that the arc connecting them was no worse than 100 times the chord length. Asymptotically smooth means the constant tends to 1 as you get smaller and smaller. So as you get points closer and closer together on the curve actually looks more and more like a straight line on small scales. And as we teach our calculus students, that means you have a tangent, except not quite. Because although it looks like a straight line, that straight line might be spinning around as you get closer and closer in. And in fact, that can really happen. There are Weil-Petersson curves that are the center that have infinite spirals on them. And so you can write down an explicit formula for an infinite spiral, which is in this class. So unfortunately, the Weil-Petersson curves are not not quite in C1. They don't have to have a tangent point everywhere. Again, we're going to come back and talk about this later on. This slide is going to be mentioned a little bit later. On the other hand, a very innocuous curve like the square, this is not good enough to be Weil-Petersson because it doesn't have this asymptotic property. If you take 2 points near a corner, the geodesic between them is √2 longer than if you go on the curve. And that √2 is the same no matter how small you get. So the ratio doesn't go to 1. And so Weil-Petersson curves cannot have corners on them. They can have an infinite spiral, we can build that in, but we cannot build an actual corner into a Weil-Petersson curve. They're a little bit too smooth for that, okay? Now, to me, because I'm a geometric function theory person, I like conformal mappings, the following result in the Takhtajan and Teo paper is the most natural. May not be the most natural to you, but we can consider the conformal mapping from the disk to the domain bounded by the curve. Now, it's a conformal mapping, so f prime is never equal to 0. If f prime vanished somewhere, it'd locally be a 2-to-1 mapping and it wouldn't be conformal. Because f prime is not 0, we're allowed to take a log of it. And now what it turns out is that your Weil-Petersson, if and only if this log f prime is in something called the Dirichlet class, which is just another name for what's called W12, things whose first derivative are an L2. So things whose gradients are an L2. So this is just a pretty standard Sobolev space, one of the easiest ones. One derivative in L2. Now I'm embarrassed that when David Mumford first asked me to take a look at Takhtajan's paper, I didn't notice this theorem. I think it's on page 72, and I kept getting stuck somewhere around page 10 or 15 or in chapter 1. So I got distracted by other things. I didn't come back to it. But then I went to this conference on random sets at IPAM. And Yilin Wang, who's pictured here, she gave the talk I mentioned. And in her talk, she listed a bunch of equivalence classes and she wrote down this theorem. And then this made a light bulb go off in my head. I'll tell you why in a second.
So
the reason why
space that you're talking about, though, seems to be with respect to Euclidean area, not with respect.
Yes, dx dy. So this is Euclidean area. So yes, before we were talking about mu being an L2 for hyperbolic area, but it turns out there's an equivalent definition for the conformal map in terms of Euclidean area. Okay.
And strictly speaking, the definition also involves the function itself being an L2, but in this case, that's obvious.
Yes. In this, yeah. So correct. Now she gives wonderful talks. So I don't know if she's given a talk yet at Stony Brook, but we'll invite her sometime and she can tell you about her own work. But basically she was studying this thing called Schramm-Loewner evolutions. And in SLE, there's this kappa parameter, which is very important. And as you take kappa going to 0, these things basically limit on something which looks like a straight line. But there's a certain way in which you can take the limit, called the large deviations theory, in which the limits are exactly the Weil-Petersson curves. So Weil-Petersson curves can be thought of as the limit of SLE curves as kappa goes to 0. And so that's what her talk was about. And that's why the Weil-Petersson class came up. And in the course of her giving the talk, she mentioned this characterization, which I should have read in Leon's book myself, but I hadn't. But the reason this was so interesting to me is because about 20 years earlier, these characters, Kari Ostlund and Michel Zinsmeister, had done the same thing, but instead of having the log of f prime being in W12, they had said, what if it's in a certain Banach space called BMO? And Peter Jones and I had characterized those curves. I won't tell you what the characterization is, but it's just that we had already solved the identical problem, but instead of using this space, using a different space. And if you knew what BMO was, you would realize that it's a more difficult space to understand than W12. It has a much more complicated structure. And so we had already solved the hard version of this. And so at the end of her talk, I said, oh, this should be easy. I mean, there should be no problem. And I was right. It only took me about 2 years to figure it out. But that's what I'm going to tell you about. This particular theorem of Petersson is actually one of my favorites. Probably the reason, at least this part of my work. Probably one of the reasons I got hired here at Stony Brook is because of this theorem and other things that we had done in the early 90s.
So here BMO is bounded mean oscillation?
It's bounded mean oscillation. I wasn't even going to get into it because it's sort of a sidetrack, but you're right. That's exactly what it is. So BMO is kind of like L infinity. And in fact, it contains all the finite LP spaces. So it's in between L infinity and all the finite ones. So the quasi-conformal theory is sort of based on L infinity. And they said, well, what if we just change L infinity a little bit? And we sort of worked out the analogous theory for that. And then WP is somehow corresponding to L2, which is further down this list. Anyway, this was what really inspired me to think about this problem. Now, if you know about the Sobolev space W12 on the disk, you might know the Sobolev trace theorem, which says if you take something on the disk in this class and restrict it just to the boundary, you end up in a class called H1 half. These are things which have half a derivative in L2. And half a derivative you can think of, well, if you have a power series like this and you took one derivative, then what happens is the n comes down. So if you took half a derivative, a square root must come down. That just makes sense. And if you compute the L2 norm of that, you get this. And so on the circle, H1 half are the functions whose Fourier series satisfy something like this. Okay, and so it follows from known results that if you're Weil-Petersson, then log of f prime is in the Sobolev space. Everybody knew this. Okay, from this you can also deduce that if you take the unit tangent vectors of your curve, they have to be in H1 half. Again, everyone knew this. But this is not quite what we call a geometric characterization, because this is one H1 half on the circle. It's not intrinsic to the curve. When you take Lebesgue measure on the circle and transform it, you get a measure on the curve called harmonic measure. It's basically the conformal image of Lebesgue measure. And these are in H1 half on the curve for harmonic measure, not for arc length. If you had H1 half for arc length, that would be an intrinsic geometric characterization of these curves. But that's not what you get from this until you think about it for 2 years. And then you can prove that, in fact, the Weil-Petersson is arc length in H3 halves. And so this is one of the main results. This is actually the last main result which I was able to get in this paper, but it's theorem number 1 in the preprint, because it's sort of the most nicest version of this. Now, Leon had already known that H3 halves was in the picture because he had shown that this infinite dimensional space has a tangent space, which is H3 halves. And so this is sort of a global version of that. It says, I mean, it was known that sort of in an infinitesimal sense, these curves are modeled in H3 halves, but this result says, in fact, they are exactly the Jordan curves for which the arc length parameterization is in H3 halves. Now, this particular thing now starts linking it up to other ideas, because H3 halves, that wasn't just invented here. This occurs in other fields. And I'll just mention one theorem, which I think is nice, in knot theory. Okay. So suppose you have a loop, and maybe think of it in 3 dimensions, because it has something to do with knots. There's this thing called the Mobius energy. Okay. Now, given 2 points on a curve, we've already talked about this. You can either consider the straight line distance between them through space, or you can consider going the long way around. Now, obviously, following the arc length is longer. So if you take the reciprocals, the reciprocal of the straight distance is going to be bigger than the reciprocal of the length. So this particular quantity here is going to be bigger than or equal to 0. And then we integrate it over all different pairs of points on the curve. And we say the Mobius energy is finite if this is finite. This is an energy on the curve which blows up if 2 points come together. If you have 2 points which are very close to touching, then this thing is infinity, but 1 over the length is still about 1. So it looks like you're integrating 1 minus infinity. And you can show rigorously that as 2 points of the curve get closer and closer, this blows up to infinity. And so what the knot theorists did with this is they took a curve that has finite energy, and then they deform it to try to minimize this Mobius energy. And if you're minimizing the energy, you're not allowing it to blow up to infinity. That means the curve never crosses itself. That means eventually you come to some kind of canonical representation of the knot, sort of its nicest embedding in three space. And so there's a lot of papers on this, and I won't go into it, but here are some of the people that were involved. The main thing I want to point out is that not every curve has finite Mobius energy. But one of these people, Simon Blott, proved that the Mobius energy that was invented in the knot theory is finite if and only if the arc length parameterization is in 3/2. So the Weil-Petersson class that Leon defines is exactly the same class that the knot theorists have been studying in the 1990s, except theirs are in 3 dimensions and his are in the plane. So that seems like an interesting coincidence to me, and I wonder if there's some explanation for that. Now, this is all very good. You're professional mathematicians, so things like Teichmuller space and Sobolev spaces and knot theory do not intimidate you in the least. But suppose you wanted to maybe devote one of your calculus lectures to Weil-Petersson curves. These approaches might be a little bit too sophisticated for that, but there's a way you can tell your calculus students what they are. And I'll tell you. So you take a finite length curve, okay? Choose a point, base point. Since it's finite length, let's say the length is 1. Let's go halfway around. That cuts the curve in half. Now let's cut it in half. We get curves of length 1/4, and then 1/8. And in these pictures, I showed the inscribed polygons we get by connecting these points up. As we connect them up, the lengths of these inscribed polygons converge upwards to the length of the curve. That's what length of the curve means. That's the definition of the length of a curve, is it's the supremum of the inscribed polygons. It turns out that Weil-Petersson is just defined in terms of how quickly that converges. And so the answer is your Weil-Petersson if and only if the distances go down approximately exponentially. That the lengths, the distances, I mean, the error you're making in the length times 2 to the n is summable. So this basically means the errors look like 2 to the minus n plus some summable factor. So it goes down a little bit faster than 2 to the minus n. So this particular definition is one of my favorites because you don't need to know what a quasi-conformal mapping is, or a conformal mapping, or a Sobolev space, or anything. It's just stated here. Now, depending on your pedigree, how you were trained, particularly if you're an analyst, this particular quantity, how well the curve approximates the length may or may not remind you of something. But when I was a graduate student, my thesis advisor, Peter Jones, had proven a theorem which allowed one to estimate the lengths of curves pretty precisely. And so when I see a quantity like this, it reminds me of his work. So here's Peter and his idea of a beta number. So let's imagine we have a piece of a curve drawn here, and we're going to take a box in the plane. And the question is, how wiggly is the curve restricted to this box? And the beta numbers measure this. So here the beta number is approximately 0. The beta number is the width of the thinnest strip containing the curve divided by the width of the curve. So it's like a percentage. And so in this case, the curve is only about maybe 10% the width of the box. So beta is pretty small, maybe about 0.1. In a picture like this, the thinnest strip is pretty big. So maybe here beta is like about 0.9. It's pretty big, but beta is always between 0 and 1. And then what Peter proved is that you can compute the length of a curve using these beta numbers. There's this formula that says the length of any curve is its diameter plus the sum of these beta squareds times the diameter of Q, where you sum over all the dyadic cubes in the plane. And you really only have to sum over the ones that hit the box. I mean, if you have squares which do not hit the curve, they don't count for anything. The betas are 0 there. And so this is what's known as his traveling salesman theorem. And so this is a pretty nifty theorem. I mean, Ra'anan can probably tell you more about the intricacies of this than I can. Peter proved this theorem in the plane, and then a graduate student of John Garnett at UCLA did it in finite dimensions, and Ra'anan in his thesis did this in Hilbert space. And this was a really remarkable result. I still find it amazing. I'd like to understand it much better than I do. But for us, we're pretty happy just to look at it in the plane. Now, because we can compute lengths in terms of the beta numbers, and we have a characterization of the Weil-Petersson in terms of the lengths, there should be a beta characterization of them. And this is it, that you are a Weil-Petersson curve if and only if the beta numbers are square summable over all cubes. So we just took Peter's criteria and you cross out the diameter term. And to me, what this means is that when you have the curve passing through a box, these beta numbers, which measure the size of the strip, are giving us a curvature measure. How close is the curve to being a straight line? So I'm not thinking of curvature as being a point-wise thing, but I'm thinking of it being associated to an arc. Given this arc, how bendy is that arc? And this condition says that when we sum over all possible positions and all possible scales, so around every point there are boxes of every scale, the curvature is an L2 after you sum or integrate over all positions and scales. And all the different characterizations of the Weil-Petersson class we know can be put into this box. They can be put into this format. Even the ones about H3/2 can be put into this box. The Mobius energy from the knot theory, they can be made to look exactly like this. All the characterizations, if you just define, if you're liberal about what curvature means, it's a measure of how far from flat you are at a certain scale and position, then all the different characterizations are versions of this. Okay, questions so far? I know we're going pretty quickly. You guys have been very quiet. If this is a calculus class, I would suspect you were watching YouTube or something. Okay. Now, I mentioned before that the Weil-Petersson class is Mobius invariant, but the beta numbers are not, because beta for a line is 0, but I can take a Mobius image and map it to a circle, and then the Mobius, for a circle need not be 0. So what I'd like to do is use hyperbolic geometry to make a Mobius invariant version of the beta numbers. And the first attack on this is to replace the straight line by disks, because circles tend to be a little bit more Mobius invariant. And the idea is to take two large circles, which are separated by gamma, but are only about epsilon apart. And now if you take a Mobius image of this, you will still get two large circles separated by gamma, although epsilon may change a little bit. So it's not completely Mobius invariant. What we want is a way of measuring the distance between these disks, which doesn't change. And the way to do that is to move into one higher dimension, to think of these disks in the plane as being the bases of hemispheres in the upper half space. So now we're working in three-dimensional space. And then we can take the hyperbolic distance between these hemispheres. And now this is Mobius invariant. Now, if I take a Mobius image of these two disks, they're going to map to two other disks, which have hemispheres, but the distance doesn't change. The hyperbolic distance doesn't change between those. And so this is going to lead us to the hyperbolic or the conformally invariant version of the beta numbers. This is also leading us into convex sets, because these hemispheres in the hyperbolic geometry are half planes. Let me just remind everybody about what convex set means. So convex set means that I have 2 points. Use a darker color. If I have 2 points, the geodesic containing them is also in the set. So 2 points in the set, the geodesic is also in it. This is not the most convenient definition of convex. There's a little better one for our purposes, which is that the complement is a union of half spaces. So the real thing that is great about convex sets, at least like in functional analysis, is that if you take a point that's not in the convex set, there's a hyperplane that separates the point from the convex set. That's the really terrific thing. And what this means is that the whole outside of the convex set is a union of half planes. And in hyperbolic geometry, this is sometimes easier to spot visually than the geodesic condition. If I'm just looking at a boundary set for the hyperbolic disk, I could check that any 2 points are connected by a geodesic that stays inside the yellow. But it's even easier and faster to see that each of the complementary components is bounded by a geodesic, and it's a half space. So when I glance at this, there's 2 ways I can tell it's convex. And sort of, to me, the neater, trickier thing is to note that the complement is a union of half spaces, hyperbolic half spaces. That's the way to identify a convex set quickly. And in the next dimension up, 3D spaces are going to be very helpful, okay? So in the next space up, we're going to talk about curves in the plane and their hyperbolic convex hulls. So what we could do, here's just an easy case of a circle. Given any 2 points, I could take the geodesic that connects them. So I could take all the different geodesics connecting all the different points. And what they do is they fill in this hemisphere. But the way I really want to think about it is that this hemisphere is a surface, and the surface divides the space into 2 pieces, the outside and the inside, and each of those is a half space. And because the complement is made up of half spaces, it must be a convex set. Now, if it's not a circle, things get a little bit more complicated. But we can use the same picture. If we have a general curve here, we can think of taking a disk which is inside the curve, its hemisphere. This is a half space, so it doesn't hit the convex hull. So the convex hull is somehow some kind of collection of geodesics connecting points, but it's a little hard to visualize what those all look like. But for every disk, I can just take the hemisphere that has that as its base, and I can take the union. And what you can imagine is I'm building like a mountain range. I'm building a big lump of sand whose base is omega. And to show you a little better computer-generated picture, here's a smooth curve, and here's the dome that is created. This is the union of all the hemispheres whose base disk is inside the curve. If you have a computational frame of mind, you might ask how I generated this picture. And there's a little trick that when you're given a domain, there's this object called the medial axis from computational geometry. It's a tree. It's the centers of all the disks which hit the boundary in at least 2 points. And this medial axis is something we can compute very rapidly. And then the hemispheres that are over these disks fill in the entire dome that I was talking about. And so when you take all those disks, you get the picture I just showed you on the previous page, this one. Now, we can also take the disks for the outside, and we can compute the complement. There are 2 complementary components. So the first one looks like that, and the second one looks like that. And if I put these both together, the convex hull of the curve is the region beneath the red and above the blue. That's the convex hull of this particular curve. I put up a few other examples, like a square. This is the lower boundary of the convex hull, and this is the upper boundary, and you put them together, you get the convex hull of the square is the region between these 2 surfaces. I don't know if these come over as nicely on Zoom, but they're pretty sharp on my screen. Hopefully you can sort of see what the 3D picture is supposed to look like. Here's another dome of a polygon. So this is the lower surface of the convex hull, and here's the upper one, and here's both of them. Now I want to show you a detailed picture, but it's hard to do these 3-dimensional drawings. So the next picture I'm going to show you is I'm going to take a vertical slice. So think of taking a line in the plane and then taking a vertical slice here. And then I'm going to show you, there's a, you can sort of think that the convex hull then is going to have some kind of slice here. So I'm going to take a 2-dimensional slice and look at this. This is the cartoon. So down here is the plane, and up here is R3. And this shaded picture is a 2-dimensional vertical slice of the convex hull. And what I'm interested in is how, given a point on one boundary, the distance to the other complementary component. So the convex hull of a curve is always some region in hyperbolic space and has 2 components, sort of the inside and the outside. And you can,
the curve is always at infinity. You're only considering curves at infinity, right?
Well, I'm considering that perhaps space. So the curve is actually here. Here's the curve, and
Right.
here's the curve. So it's sort of coming around here in the plane. I'm showing a 2-dimensional slice of it. So
Which is at infinity for hyperbolic space, and then you're taking its
yes,
convex
at
hull.
infinity for height, exactly. Okay, so what you can think of is that this point has a supporting plane, which looks like this, which is based by a disk here. And this one has a supporting plane out here, which corresponds to a disk on the outside. And so the picture I was showing you before of how far apart are the hemispheres, that's exactly this. And then what we want to do is basically add this up everywhere. We want to integrate that over hyperbolic area on these boundary surfaces. And sure enough, the thickness, the delta squared, is finite if and only if you're Weil-Petersson. And so this is clearly a completely invariant notion. If you were to take a Mobius transformation, it becomes an isometry of hyperbolic space. Everything in sight is just defined in terms of hyperbolic geometry. So none of the numbers change whatsoever. And so this is the hyperbolic version, the conformally invariant version of the beta numbers. Now, one awkward thing about this, it's not quite as pretty as it could be, partly because you have to integrate over the convex hull boundary. And there's two boundaries. There's one here and there's one here. You could integrate over both of them or just one of them. It doesn't really make any difference. It would be lovely, though, if we didn't have to make this choice, if there was just one surface that was in the convex hull maybe and came down and hit the curve. So is there a natural choice of a surface in hyperbolic space which has a given curve as its boundary at infinity and lies inside the convex hull? Turns out the answer is yes. At least half the audience knows this. This is a minimal surface. Okay, so just as a really quick review, capital K will denote Gauss curvature. Kappa 1 and kappa 2 will be the principal curvatures of a surface. If they are opposite and if they're equal but opposite in sign, that means we have mean curvature 0 and we have a minimal surface. In that case, the Gauss curvature is -1 minus kappa squared. And I believe one of the members of the audience proved this theorem, that every closed Jordan curve bounds a minimal disk, and this minimal disk is inside the convex hull. So instead of integrating over the convex hull boundary, we could just integrate over this minimal surface. That turns out to give exactly the same answer. Or it gives, it's finite if and only if the other one is finite. Minimal surfaces can be a little tricky. I copied this a picture from Mike's 1983 paper. This particular curve is kind of fun. It's almost two concentric circles joined by a little tube. You can see the little tube in the picture over here. But this bounds a second minimal surface. So it's not unique. So you don't have to have a unique surface bounding a particular curve. So I'm just sort of fascinated by that. And Mike gives examples of fractal curves for which there are infinitely many minimal surfaces which are asymptotic to a given curve. That's a different story, which we won't get into today. What I'd like to do, though, is figure out what this minimal surfaces sort of looks like globally. And in particular, I'd like to estimate the principal curvatures. Now, the claim is that this took me like half a year to find. But what I want is that the principal curvature, sort of how much these things bend, is dominated by delta. So we know that we have a surface, a minimal surface. It's trapped between two almost parallel planes. These planes are only delta apart. They're very, very close. Now, on the bottom picture, I speculate that maybe a minimal surface could oscillate wildly, even though it was trapped between two parallel planes. Turns out that can't happen. The idea is that a minimal surface is a lot like a harmonic function. If you have a harmonic function, which has small L infinity norms, so it's sort of trapped between epsilon and minus epsilon, you can use Harnack's inequality to say that the gradient and the second gradient are actually also order of epsilon. So you can get estimates on the derivatives from knowing the sup norm of the function. And this also works for minimal surfaces that this fellow, Andre Seppi, had showed if you take the distance of this minimal surface to one of these planes, it satisfies a certain elliptic equation. And then using the Schauder estimates, he could bound the gradient of the minimal surface in terms of how far away from the plane you are. And you're not far away from the plane, you're only delta away from the plane by definition. So these principal curvatures are bounded. Well, if delta is square integrable and kappa is bounded by delta, kappa is also square integrable. And so your Weil-Petersson curve, if and only if you bound a minimal disk with finite total curvature. So the Gauss curvature over the whole surface integrates out, or these things. Now, it had been a question that was asked in the early 90s, whether the boundary at infinity of such a surface had to be a C1 curve. And the answer is no, because I already showed you that a Weil-Petersson curve could indeed have an infinite spiral built into it. And so the answer to this question is no, that the boundaries of surfaces of finite total curvature don't have to be C1. Now, the if and only if I haven't quite explained. What I explained was that if the delta squared thing was finite, if that integral was finite, then kappa was. So if you're Weil-Petersson, we've done a long chain of implications, which implies where total area, the total curvature is finite. But I need to get back to the original Weil-Petersson class to complete the circle. I have one more step to complete the circle. So I need to know that if I have this condition, the curvature squares are integrable, then the boundary curve at infinity is one of these Weil-Petersson curves. And remember, I told you you needed to remember a slide. You needed to remember that Weil-Petersson curves were the fixed point curves of involutions. Now we're going to use that. And we're not going to do any work because it was done for us already. Here's another cartoon where the plane is the base and R3 plus is up here. And the surface is this thing. So this black line is actually a two-dimensional surface seen sideways. And I'm trying to illustrate here what the Gauss map is. If you take a point on the curve, on the surface, you can go, there are two perpendicular directions. And you can follow that geodesic down in either direction. And so you get a point Z over here and a sort of corresponding point over here. And if you choose a different point and follow these, you get a W and a W prime. And if you follow these, you get here, and it's fixed here. So the Gauss map defines a mapping from one side of the curve to the other side that fixes this. It's an involution. Is it one of these quasi-conformal involutions? Well, Charlie Epstein proved that it was back in 1986. He showed that if you have this finite total curvature condition, then the reflection across the curve you get, the dilatations are square integrable for hyperbolic area. He didn't say it this way, but it follows from his result. So what he shows is that if we have this finite total curvature, then we get back to that slide. That was what, 20 slides ago. And so we've made a circle. We've gotten back to the original definition. Now that is almost the theorem, but we have a few minutes left. There's one more thing I would like to tell you about if you have the patience. Do you think you could stand here maybe 4 or 5 more slides?
Sure.
Okay. So this has to do with isoparametric inequalities. Now, I can't compare the area and the length of my whole surface because it has infinite area, and the boundary is at infinity, it has infinite length. But if I truncate the surface at a height t up above the infinity, so I'm thinking of the upper half space model here, then the part of the surface that's above t, that's a compact surface. It has a compact boundary. So it makes sense to talk about the length and the area of that boundary to compare which one is bigger. And because we're in negative curvature, because it's a minimal surface, the curvature is less than -1, there are isoparametric inequalities for such surfaces. And they said the length is always bigger than the area plus a topological factor, 4 pi times the Euler characteristic. Okay. And so if the surface is kind of wiggly, it has some curvature, this gap can be pretty big. But for the half plane, where there's essentially it's as flat as possible, for a hyperbolic half plane, in fact, this is sharp. Okay. Now the question is, what about on the other side? Could we get a bound, an upper bound, which is an additive factor? So this is saying as we take our truncations further and further out, it's sort of like saying that length and area grow at the same rate. This is sort of a Cheeger kind of inequality. We're saying asymptotically is the Cheeger constant 1 in a very precise sense. And this has a name. This is called renormalized area. So this is something that Graham and Witten had proved is well defined, that if you take these truncations and you take the area above the truncated curve and subtract the length of the truncated curve and take the limit, that this is well defined, that this limit actually exists and it's conformally invariant. That's the hard thing, that if you have a curve and you map it by a Mobius transformation to some other curve, this number does not change. That's not obvious, but that's what they showed. I'll put in these words because somehow this has something to do with quantum entanglement and the ADS-CFT correspondence in a way that I don't understand, but I sure wish someone could explain to me. I would love to understand it. You know, you hear words that saying, well, if this curve in the base here separated a quantum state here and a quantum state here, then the area of the minimal surface separating them, you know, would give you the quantum entanglement in the same way that the area of the event horizon of a black hole, you know, tells you something about the quantum state of the black hole. And I don't know what any of those words mean, but
is this supposed to make
pretty
sense?
Impressive. Okay, so the reason I mention this is because I spent about 6 months trying to prove the following and finally did, that the surface has finite renormalized area if and only if the boundary curve is Weil-Petersson. So in some sense, these curves should be good for something in physics. I don't know quite what, but they ought to be good for something because these are exactly the things. Now, in the if and only if there are 2 directions, and the harder direction is to go from that you have finite renormalized area to being Weil-Petersson. So that requires reading the literature. I had to go back as far as the 1940s and read a bunch of papers, but eventually I learned enough to prove this. The easier direction, there's one quick proof in 3 space and a harder, more indirect proof in higher dimensions. But let me just show you the thing that works in 3 space, because it uses Gauss-Bonnet. And I mean, for some of you, this may seem ridiculous, but I never use Gauss-Bonnet. I mean, I don't have any papers where it played any role. And so it's kind of exciting to me to be able to use it some place. And so here's my application of the Gauss-Bonnet theorem. We're interested in the area of the surface minus its length. And so the area we can just compute as the function 1 integrated over the surface. I think that's agreeable to everyone. And the length of the boundary is the function 1 integrated over the boundary. Well, no one's objecting to that either. Then we do the classic math trick of adding a term and subtracting the same term. Everyone likes that. And then 1 plus kappa squared, that's the negative of the Gauss curvature. I mentioned that before. Now we use Gauss-Bonnet. When we integrate the Gauss curvature, it becomes a topological term and an integral of the geodesic boundary. And now we rearrange. We have the topological term, we have the integral of the principal curvatures, and then we have this annoying term of the geodesic curvature minus 1 on the boundary. And what we really want is this to go away. We want that to be 0. But that turns out to be the case, because after thinking about this, I mean, maybe take you guys a little while, it took me a few weeks, I was able to prove that the geodesic curvature is bounded. So if you have a minimal surface inside a convex hull, and the convex hull has this thickness criteria, then the geodesic curvature is 1 plus order of delta squared. And we're subtracting the 1. So this is order of delta squared, and we're integrating it over the boundary. What you can think of is that you have this surface, you have this boundary. What you're really doing is integrating delta squared over a unit length strip. But delta squared is an L2 over the whole surface. So as this unit strip goes off to infinity, that integral goes to 0 and it drops away. And what we get is that the renormalized area is given by a topological factor minus the integral over the surface of kappa squared. And this is a pretty nice formula, I think. I cannot claim credit for it completely, because this was a theorem also of Alexakis and Mazzeo. And so I had spoken to Rafe maybe about 2 years ago, and that's how I learned of this theorem. And I read this paper of theirs from 2010. It was very annoying to me because they assume that gamma is C3 alpha. Because in their proof, what they do is they assume that this minimal surface near the boundary is locally a graph. So they have to assume that the boundary curve is smooth enough that the minimal surface is a graph. And in order to control the curvature terms, they do a power series expansion of the defining function, and they need at least 3 of the terms to be well defined in order to do it. And so they need they need to know that the boundary curve has some smoothness, but the statement doesn't have any smoothness in it. It says nothing about the boundary. And this was driving me crazy. Every time I read the paper, it was annoying to me that they made this smoothness assumption. And so I spent a long time looking up differential geometry articles on the internet. It's very hard to find a textbook on the internet. And all the journals articles assume you know what everything means already. It's sort of hard to reverse engineer all the definitions that way, but eventually you can do it. And so my proof of this is basically intrinsic to the surface. It involves various isoparametric inequalities on the surface, because this thing is, I mean, renormalized area is really an isoparametric kind of quantity. And so my proof of this doesn't refer to the boundary curve at all. It never comes up in the proof anywhere. It's just in terms of this curvature condition. And so in my results, it's just for any closed curve, a fractal, anything. What happens though is that both these sides are finite if you're Weil-Petersson. These are bigger than minus infinity. And if you're not Weil-Petersson, it's equal to minus infinity. And that's the theorem. Now, this is a list of 20 different characterizations of these curves. And we've talked about a couple. We talked about log of f prime being in the Dirichlet class. And we talked about beta numbers. We talked about the thickness of the convex hull. Here's our founders, by the way, Andre Weil and Hans Petersen. I can hardly keep track of all of these different definitions in the paper. So I had to draw a diagram. And this is the proof diagram of how the different things imply each other. The tour that we've been on today roughly goes something like this. I started you out over here, and this thing, this was the H3 halves definition up here. This was the beta numbers. These were the epsilons. This is the delta. This was the kappas being integrable. This was Charlie Epstein's thing. This is the biLipschitz, and this is the renormalized area over here. So I've stared at this diagram so long now, I know what all the different things mean. But roughly what we did was we talked about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of the 20 characterizations. And so I told you I would tell you half of a theorem today. And we just about fit it in, half a theorem. Well, thank you for listening. I appreciate it. I hope it wasn't too dreadful, but you were a very patient audience. I appreciate it.
Thank you. Any questions?
That was a beautiful talk.
Chris, you
So,
mentioned something about the Kähler geometry of this moduli space, or this
Right.
type of space.
So that's one of the things I'd like to learn more about. I'd mentioned David Mumford a couple of times in the talk. He actually also is a big inspiration to me. He had originally mentioned this problem as one I should work on. And so when I started to make some progress on it, I kept him updated on what was going on. And he kept making constant, suggestions and improvements. The theorem about the arc length parameterization being in 3 halves, he actually pointed out that I proved it. I proved some other things. And he emailed me and said, I think you proved the arc length parameterization is in 3 halves. And I wrote back, no, I don't think so. And then he wrote back, are you sure? And I said, well, maybe. And after about an hour, I said, yeah, of course I proved that. Yeah, that's follows from what I've done. I just had never thought about it that way. He is a really big fan of the fact that the Weil-Petersson class forms a Kähler-Einstein infinite dimensional manifold. I don't even know enough about finite examples to realize that an infinite dimensional one is a particularly nice object, but he was saying it's sort of miraculous that certain things happen. I would like to understand what the miracle is. I mean, I know yes, he said many, many nice things about it, but apparently you have to have negative curvature, but the curvatures have to flatten out at a rate which is sort of L2 summable at infinity. And I guess a lot of things have to work out just right to make it happen. Perhaps Leon could say something about.
Right. Isn't it Alfors who proved the Kählerness of the Teichmuller space of in this finite dimensional setting? Is it related to that?
Well, let me explain. In finite dimension, Alfors proved and Weil that Weil-Petersson metric is Kähler, but it's not Kähler-Einstein. Alfors proved that all sectional curvatures are negative, and Scott Wolpert gave beautiful formulas. But then for the universal Teichmuller space, we proved with Lipeng that it's Kähler-Einstein because it's in a rigorous sense, and all curvatures are negative, exactly same things as for finite dimensional spaces. But actually, I have a question to Chris, because what you said about this renormalized volumes and areas is very interesting, because this happens in finite dimensions. And also for this Teichmuller space, Kähler metric has a potential, which is what Ilin Wang calls Loewner energy. This we call it S1. It's sum of Dirichlet energies. And this in finite dimensional case, similar object is a renormalized area, can be interpreted, as renormalized volume. So my question is, maybe you already proved that this functional S1 is renormalized volume. Would be very interesting to see precisely.
It could be one of the things I proved without realizing it. That happens, as I gave you the example already that David pointed out.
This, because in finite dimensional case, we're using Epstein surfaces are also used. So probably you proved this. This is very interesting. So maybe you.
Well, I would love to discuss it because there are these connections which seem fascinating, but I don't know where to take them or even what all the words mean. And somehow reading through a couple of volumes of differential geometry textbooks isn't really that appealing to me. I'd sort of like someone who knows the answer to tell me exactly the pieces I need to know to understand the answer. That may take a little while.
Already proved, because it's kind of, in finite dimensional case, it's very simple. You have a Riemann surface, then you say uniformized by quasi-Fuchsian group. Then you consider corresponding hyperbolic three-manifold, which has infinite volume. Then you regularize the volume exactly as physicists were doing, using Epstein surfaces, and you get the Kähler potential for the finite dimensional.
That's interesting. I'd like to understand the physics better, because your work was motivated by string theory, you've told me.
Well, not really.
The renormalized area is somehow connected to
area, it was, yeah, we can
physics.
discuss. Yeah, this is very interesting. What you
A third thing which I didn't mention here, when I gave this talk at MIT last week, I mentioned it more there, but there was this Mobius energy for knots, which had to do with, you sort of, one way of interpreting that is to put an electrical charge on the curve, and the charge wants to repel itself. So it doesn't want, the curve doesn't want to cross itself because of this repelling force. When you look at the potential in the Mobius energy, it's actually electrostatic repulsion in dimension 4. So the energy has a 1 over x squared singularity. So it's a 1 over inverse cube law for the repulsion. And 1 over inverse cube is 4-dimensional electrostatics. So these curves form a natural class for electrostatics in 4 dimensions. They also form a natural class for knot theory in 3 dimensions and a natural class for loops in 2 dimensions. And my characterizations, the geometrical ones, all extend to all finite dimensions. So anything that doesn't mention a conformal mapping, the beta numbers, the H1/2, the minimal surfaces, the renormalized area, those all go up to all finite dimensions for curves in higher dimensions. They can all be extended. So I don't know, does this curve has a natural interpretation in 5 dimensions or 17 dimensions or 1013? I mean, is there a sort of a natural problem for which this solves in every dimension you can think of? And then I'm trying to get Run-On or one of his students to solve this problem in Hilbert space.
right.
Either he has to read my paper or I have to read his thesis.
Right.
Whoever breaks down first, I think will solve that. But yeah, so I find these connections, to physical things kind of tantalizing, but yeah, I don't understand them, but it's sort of like there's something there. It's annoying, like at the back of your mind, like, why does this thing pop up? To my mind, the answer is that this class, Weil-Petersson, is a very natural class of curves based on a very natural metric on L2.
Right.
And although the quasi-conformal theory has a long history going back almost 100 years, it's based on L infinity, the soup norms of the dilatations. And L2 is arguably a much easier and more natural space than L infinity. Almost any problem you ask, most of these Weil-Petersson theorems have analogs that were previously known for quasi-circles. But the quasi-circle says there's a necessary condition and a sufficient condition, but they don't match. But the Weil-Petersson analog, it's if and only if. You have a matching condition, you get a much tighter, nicer.
But the metric that you're talking about is just the L2 metric on the joining vector fields, all right? Is that correct?
I think I'll let Leon answer that. So the metric is, it's hard for me to give Leon's original definition, but I mean, he talks about infinitesimal deformations of a curve, and you put a norm on that, so you can put a norm on the tangent space of the loop space, and you integrate that. And in certain directions, the integral is infinite, so you can't go that direction. But in certain directions, you can. All of my work is based on these more mundane definitions involving the dilatation being an L2 or the quasi or the conformal mapping, because those are things I know how to deal with explicitly. And his definition in terms of the charts, and that,
No,
I have a hard time manipulating those directly in my mind, and so I avoid it. I don't know, Leon, you want to say something?
We define this as a Hilbert manifold based by charts. Each chart is modeled on a Hilbert space, and the Hilbert space are very simple. It's L2 functions on a disk with hyperbolic area. Their norm gives the Kähler metric. Yeah.
Is the metric complete as a metric space?
No, it's not clear. Probably not, like in finite dimensional case, probably not.
Right.
Although
Well, I don't quite understand Mike's question. I mean, when you restrict to the smooth curves, it's not complete, but the Weil-Petersson class is by definition the completion of the smooth curves in this metric.
Well, you're
Is
sort
that
of
not what you were asking?
So I'm asking if it's complete in the sense that It's
Imagine,
think of
John,
some kind of
I
domain,
don't
and
know.
whether the domain is
Okay, maybe a different word, use the word complete than I was thinking of.
Different word, exactly, Chris. Yeah, what Mike was asking, like in finite dimensional space, Teichmuller space, Weil-Petersson Keller metric is not complete.
right,
Isn't it?
right.
And probably same holds for infinite dimension, although we don't know. We
But
don't-
then
Closure
so
you're thinking
it's
about
not
is a kind of
complete.
local closure.
If there's
local
kind of a
heat.
boundary, then you'd expect there'd be some further degenerations of the Weil-Petersson class at the boundary.
Probably. This would be very interesting to understand globally what's going on for this infinite dimensional manifold. It's not clear. We don't know.
Oh. I have a very elementary question. In one of your characterizations, arc length and H3 halves,
Yes.
that seems to be intrinsic to the curve. I don't see how it prevents the curve from wanting to self-intersect.
Well, that's because I was a little sloppy. The actual characterization, if you go to the paper, is that the curve is chord arc and H3 halves.
Okay.
So I just was not stating the theorem exactly precisely in order to make things move more smoothly.
Okay, great.
So it is true though. Yeah, okay. Yeah, it's chord arc and H3 halves, and the chord arc constant and the H3 halves constant together give you the sort of the Weil-Petersson size of the curve. So you're right. That was very sharp. I've given this talk 4 or 5 times, and you're the first person to ever point out that I was sweeping something under the rug there.
Oh.
That was
I'm
you
glad
win a prize for that.
I'm glad you cleared it up. That's the important thing.
No, that was actually a point that puzzled me. Because in the knot theory,
Yeah.
they keep saying that this H3 halves condition implies your chord arc. And I knew this wasn't true unless you assumed chord arc, and it was driving me nuts as to why they were saying this. And the reason they were saying it is because they were assuming it was a Jordan curve. And if you assume it's a Jordan curve in H3 halves, that means it can get very close to itself. But the Jordan hypothesis means it doesn't actually touch.
Right.
And so there's a chord arc constant depending on it not touching itself, which is huge. But there's a more quantitative thing if you assume it. So this actually took me a while before I was also reading these knot theory papers and trying to make sense of it. Everything I learned in mathematics, I somehow have to turn into my own internal language so it makes sense to me.
I think we all do. So,
And
our own
this
way.
took me a while.
Yep. Huh.
So here's a different question.
Yes, Matt, what's up?
So with the quasi-circles that aren't Weil-Petersson, like, is there any significance to them or any way of, say, cataloging them?
Well, one of the questions Leon asked was to find a section. So the loop space has been sliced up into these, sort of components. Make us a dictionary. Give us a list of curves, 1 per component, and no duplicates.
So that's not known, you're saying?
We don't know how to do that at all. There's something very similar. Stefan Rode 10 or 15 years ago created a list of quasi-circles so that there was 1 per biLipschitz class. Every quasi-circle is biLipschitz equivalent to 1 thing on his list, but all the things on the list are not mutually biLipschitz equivalent. So it's a section of quasi-circles modulo biLipschitz things. But I don't even know how to begin to formulate what a section would be. Now, the finite dimensional Teichmuller spaces they live inside the Weil-Petersson class. In those cases, you have a Fuchsian group acting on the disk. And the dilatations that correspond to the mappings are invariant under this group. So they're sort of periodic for some hyperbolic tessellation, like the pictures you see of, the Poincare disk. Every curve you get is either a circle or a fractal. As soon as it's not a circle, the limit set becomes a fractal, so it's not in Weil-Petersson. And those finite dimensional things somehow live transverse. So those are picking out sections. I think all of them are distinct, that if you have 2 different deformations of the group, either they're identical or they're in different connected components. I haven't proven that, but that would be probably a good topic for a student or someone, or maybe not even a student. I don't know how hard it is. It might be quite hard. I don't think so. So that is sort of picking out, so the finite dimensional spaces pick out kind of finite dimensional sections, I believe. But yeah, in general, what I've given is a test that tells you if two things are in the same component of the circle. Okay. But when are two things in the same component as the square, or the same component as the von Koch snowflake, or the same component as something else? That hasn't been worked out. I was actually talking to Dragomir Serik a week or two ago, and he has some graduate students, and I suggested they work out everything that's equivalent to a square or any polygon. I think what's going to happen there is that when you have a polygon, you have vertices connected by straight edges that meet at certain angles. And you're going to take Weil-Petersson arcs, which we sort of define. We define closed curves, but you can imagine arcs instead. And it's basically going to be a polygon made out of arcs, of Weil-Petersson arcs instead of straight lines. I think that's going to be the answer for the components of polygons. But I said, why don't you assign that to one of your students and see what they can do? But right now we have this huge infinite collection of components, and we sort of understand one of them, kind of.
So a question with that, because if you take just a given quasi-circle and compose it with a Weil-Petersson one, like, does that stay within the same class necessarily?
I think so. I asked Leon this once. So I said, Leon, if you have a closed curve, a quasi-circle, and you apply a quasi-conformal mapping to it, so the dilatation is an L2 of hyperbolic area for both sides, is the image in the same connected component? And he wrote me back saying yes. So is that right?
Yeah,
Do you remember
probably.
that?
I cannot say it right now, probably, but it's a
Probably,
very,
yeah. So it's one of those things which is so true
how
that we
you
believe
prove
it, but not so true I would use it in a written proof without checking it. So it's sort of one of these things, you don't get any credit for proving it, but you can't use it unless you do prove it. I mean, it's sort of, you know, on the boundary there, but I think that's true. But that question would make sense even if you're not a quasi-circle. If you had an arbitrary Chord Arc curve, you could say, what things can you get from it under the same condition? I mean, I don't know.
For instance, what you get if you consider a square and all points in a component of a square. Can you classify them?
Yeah, I just had mentioned a possible characterization of those. But yeah, that would be interesting.
So part of the story in terms of the motivation and background literature was about knots in three space rather than curves in the plane.
Right.
And
that's something I learned kind of late in the story, but to me, it's sort of so fascinating that the same class was invented 20 years ago for completely different reasons in a different dimension. But the Mobius energy, although it was invented in three space, it still makes sense in the plane or in four dimensions. You can define it. And the characterization in terms of H3 halves is the same in every dimension. That doesn't change. So the Weil-Petersson class is an answer in search of more questions. So it answers a couple of questions, but there's probably more to be found. It's sort of like the wave equation and the Laplace equation. They're such fundamental things that they pop up in lots of different places. And somehow the Weil-Petersson class is a fundamental object, which we're going to discover, I think, has been invented in the past under different names. And we haven't realized that yet, or it's going to turn out to be useful. In some sense, it should have been studied before quasi-circles because L2 is easier than L infinity. And so in some sense, we should have done the L2 case first.
so, but is there, when you look at maps of circles into higher dimensional Euclidean spaces, is there an analogous story where you construct a disk in hyperbolic space that has that
I don't know. So if you remember, let me just share my screen again for 1 second. It's fun to see your page, your faces, but let me just show you. You remember this complicated diagram of the proofs? I didn't explain about the pink and the blue and the yellow. The pink are all the conditions that involve maps of the circle. And the blue were all the conditions that involved curves in Rn. And the yellow were all the things that were about surfaces in hyperbolic n space, okay? And so the things on the circle are kind of restricted to the plane. But if you draw a line here, in the preprint, I was very careful to make sure you could reach all the blue and yellow things from each other, but without ever passing through the pink. So you can go from 8 down here, and you can go around, and you go up, and you can, it's a connected component here. So all the higher dimensional things are equivalent to each other, even without knowing anything about maps from the circle. Now, does it make sense to embed if you have a curve in higher dimensions, can you think of it as the boundary of a disk and a mapping onto that disk, sort of like a minimal surface? Probably, but I haven't explored that yet. So that is something which could be done. I'd shied away from that because some of we people who think about quasi-conformal mappings in the plane shy away from higher dimensions because there's no measurable Riemann mapping theorem. We don't have this wonderful theorem that says that for any measurable structure, we can build a QC mapping. It doesn't work in 3 dimensions. And so kind of shy away from that. Like, I might make a mistake. My 2-dimensional intuition might lead me astray. In higher dimensions, I prefer to think about biLipschitz mappings, which can clearly be defined. And so I'm careful in the plane to give biLipschitz equivalent versions of all the results, which do extend to all higher dimensions. So one of the fun things, I got to exchange some emails with John Morgan. I think I annoyed him after the 5th or 6th one, because when you have this biLipschitz, the curve is fixed under a biLipschitz involution, and that extends to higher dimensions. But in 3 space, you have to restrict the involution to an annular neighborhood of the curve, because the Smith conjecture says that if you're the fixed point of an involution on all 3 space, you're unknotted. And there's no reason when these H3 half curves can't be knotted. Mm-hmm. And so it took me a while to understand that, but he was very patient in sort of, every time I came to a step with a proof of why that was working, he would sort of answer my email and tell me not to worry about it. So lots of different things come in, which I learned a lot doing this. And in the fall, I taught a topics course on this preprint, and it took me the entire semester to go through the diagram, which I showed you. I mean, we had some, days when the pipes were leaking, I had to cancel, and a few things, had some guest lectures, but basically, there are 20 equivalent conditions, and I spent 3 days giving an overview, and then 22 days proving the 20 implications. So basically 1 implication, per lecture. And I appreciate the students. I mean, some of the people who attended are here, and they helped me. I waited to submit the paper till after the course was over, because I figured I would find a lot of typos in the course of it. And, the people who attended, their proofreading and their questions helped improve the final thing. I mean, long papers are hard to write, and they're terrible to referee and to read. And so I was trying to make the paper almost as fun and entertaining as I try to make the talk, except there's not color pictures, because I know journals probably frown on that. Yeah, I'm always looking for more feedback. This is just the beginning of some story, which I don't know where it'll go. But to me, there's lots of fascinating things and little, why does that work out that way? Like, lots of coincidences bother me in math. When 2 things, you get the same answer by some calculation, I always think, well, there must be some conceptual reason to explain why that happens. And when you have, this class coming up in these problems like knot theory and Teichmuller theory and renormalization, makes me think, is there some connection between those topics that I didn't know about before? So I'd really like to learn more about that. I certainly appreciate any feedback. I mean, we don't have to hang out here. You've been very patient, but
well, it was a
if
great.
you want to talk or send an email or something, I'd certainly like to hear people's, ideas for what's going on here.
We can discuss later. It's a great talk.
Yeah, why don't we give another round of applause? Huh?
Good talk,
thank you.
Chris. Really nice.